So today I'm gonna talk about section 1, that is type of organic reaction. There is three types of organic reaction. There is addition reaction, substitution reaction, and elimination reaction. For addition reaction, two molecules combine to form a single product with no atom loss. A common example is hydrogenation, halogenation, hydration, and hydrohalogenation. For substitution reaction, one atom or group replaces another in a molecule. There is two main types of substitution reaction, that is bimolecular substitution and unimolecular substitution. For elimination reaction, a single molecule splits into two products. Common example, dehydrohalogenation, dehydration, and dehydrohalogenation. Example for addition reaction is hydrohalogenation of ethene. For his reaction type, it was called electrophilic addition. Its reactants is ethene, and reaction condition is no solvent need. For product structure, it's gonna be bromoethane. For example, for substitution reaction is hydrolysis of chloromethane. Reaction type is below molecular nucleophilic substitution. Its reactant is chlomethane plus hydroxide ion. Its reaction condition is ethanolic solution of a strong base heat under reflux. Product structure gonna be methanol. Lastly, example for elimination reaction is the hydrohalogenation of 2-bromopropane. Reaction type is below molecular elimination. Its reactant 2-bromopropane. Reaction condition strong base in ethanol heat usually under reflux. Product structure is propane. The concept of a reaction mechanism is the step-by-step sequence showing how a reaction occurs at the molecular level. Mechanism gonna explain how bond break and form, the role of intermediate and transition states, the sequence of elementary steps, and lastly the energy change throughout the reaction. Elementary step in reaction mechanism is unimolecular step, that is involve one molecule undergoing a change. Second, termolecular step involves three molecules, and lastly bimolecular step involves two molecules coming together. Example for addition. Example for a reaction mechanism is addition of HBr to ethene. The double bond in ethene attacks the hydrogen atom in HBr, forming a carbocation intermediate. The bromide ion then attacks the carbocation to produce bromoethane.
Definition of alkene. Alkene are unsaturated hydrocarbon containing at least one carbon-carbon double bond. The general formula for alkene is CnH2n, where n is the number of carbon atom. The simplest alkene is ethene, C2H4. The important reaction of alkene is alkene undergo a rich variety of reaction due to the reactive bond. Major categories of alkene reaction include addition, oxidation, reduction, polymerization, and rearrangement reaction. There are three types of electrophilic addition reaction, which is electrophile attack, carbocation formation, and nucleophile attack. Electrophile attack is the electron-rich bond attacks an electrophile, forming a carbocation intermediate. Carbocation formation is the most stable carbocation form according to Markovnikov rule, and nucleophile attack is a nucleophile attacks the carbocation to complete the. Next is Markovnikov rule. Markovnikov's rule states that in the addition of H adds to an unsymmetrical alkene, the hydrogen attached to the carbon with more hydrogen atom, while the halogen attached to the carbon with fewer hydrogen atom. This rule is based on carbocation stability, tertiary carbocation, secondary, primary, and methyl. The most stable carbocation form preferentially. Alkyl groups stabilize carbocation through hyperconjugation. There are three types of physical properties of cis-trans isomer, which is boiling point, melting point, and stability. In boiling point, trans isomers typically have higher boiling point than their cis counterpart due to greater molecular symmetry and stronger intermolecular forces. In melting point, trans isomers generally have higher melting point because they pack more efficiently in crystal lattice due to their linear shape. Last is stability. Trans isomers are generally more thermodynamically stable than cis isomers due to reduced steric hindrance between substituents.
Alkynes are a class of unsaturated hydrocarbons that contains at least one carbon-carbon triple bond. Alkynes are named using the IPAC system, similar to alkanes and alkenes, but with the suffix "-ine" to indicate the triple bond. We have to identify the parent chain to find the longest continuous carbon chain that includes the triple bond. Secondly, number the chain from the end closest to the triple bond to give it the lowest possible number. Then, the locand for the triple bond is the number that placed either before the parent chain name or the latest IPAC convention before the suffix. Next, name and locate any substituents, listing them alphabetically. For terminal alkynes, they have the triple bond at the end of the chain. For internal alkynes, they have the triple bond in the middle of the chain. As for compounds with double and triple bonds, the chain is numbered from the end nearest to the first bond if the multiple bonds are equidistant. From the ends, the double bond takes priority to the lower number. The suffix used is A9. Okay, the preparation of alkynes. This process involves two consecutive E2 elimination reactions, removing two molecules of hydrogen halide from a dihaloalkane to form a triple bond. Starting material can be vicinal dihalides. The two halogen atoms are on adjacent carbon atoms, often can be prepared by the halogenation of an alkene. As for geminal dihalides, the two halogen atoms are on the same carbon atom. Okay, the key reaction of alkynes. For addition reaction, the general mechanism is alkynes typically undergo addition reaction where the end bonds are broken, allows new atoms to be added to the carbon atoms. This can lead to the formation of alkenes or alkanes depending on the reaction condition. For hydrogenation, in the presence of a catalyst like platinum or palladium, alkynes can be hydrogenated to form alkenes and further to alkanes. For example, 2-butene can be converted to butane through hydrogenation. Thirdly, halogenation. Alkynes react with halogens like bromine and chlorine to form dihaloalkanes or tetrahaloalkanes. For instance, the reaction of 1-butene with bromine results 1,2-diprobutane. The key reaction of alkynes. Firstly, deprotonation. Terminal alkynes can be deprotonated to form acetylide ions using strong bases such as sodium amide. This reaction is significant as acetylide ions are strong nucleophiles and can be participate in nucleophilic substitution reaction with primary alkyl halides. As for industrial and practical application of alkynes, one of the example is welding and cutting fuel, which is acetylene is the most famous for its use in oxyacetylene torches. When acetylene burns in pure oxygen, it produces a flame that reaches exceptionally high temperature, up to 3,000 derajat Celsius or 6,000, making it the hottest burning common gas mixture used for welding, cuttings, and heat treating metals.
Stereochemistry is the study of how atoms are arranged in three-dimensional space inside a molecule. This 3D arrangement is very important because it can change the chemical and physical properties of a substance even if the formula is the same. Let's start with the difference between constitutional isomers and stereoisomers. Constitutional isomers have the same molecular formula, but the atoms are connected in a different way. For example, butane and isobutane. They both have the same formula C4H10, but their structure are connected differently. Stereoisomers, on the other hand, have the same formula and the same connection, but their atoms are arranged differently in space. A simple example is cis-2-butane and trans-2-butane. They look almost the same, but their 3D shape make them behave differently. Next is chirality and enantiomers. A molecule is called chiral when it cannot be placed on top of its mirror image, just like your left and right hand. They look similar, but they are not the same. Usually, chirality happens when a carbon atom is attached to 4 different groups. Enantiomers are a pair of chiral molecules that are mirror image of each other, even though they look like they can act differently. For example, they can rotate like in opposite direction or have different biological effects. A real-life example is lactic acid, which exists in R and S forms. Another famous case is the thalidomide drug, one for war as medicine and the other form cause birth defect. Now let's talk about optical activity. Because chiral molecules are not symmetry, they can rotate plane polarized light. If the light turns to the right, it's called dextrorotatory, and if it turns to the left, it's called levorotatory. Some molecules like glucose show optical activity because they are chiral. Finally, we have the stereomers, miso compound, and race mixture. The stereomers and stereoisomers that are not mirror image. For example, the cis and trans form of 1,2-dichlorotane. Miso compounds have more than one chiral center, but are not optically active because they have internal symmetry. And race mixture contain equal amount of both enantiomers, so their light rotation cancel out and they are also optically inactive. In conclusion, stereochemistry helps us understand how the 3D structure of molecules affect their properties, reaction, and even their effect on our bodies. It shows that a tiny change in structure can make a big difference.